Okay, today what we're going to do is talk about the kinetic theory of gases, and this will be filling in your note sheet that I gave you. The kinetic theory of gases, it says that the ideal gas model explains how ideal gases behave. So what we're learning a little bit about is we've learned about gases. We started with it in elementary school and middle school, and we're just adding on to that and understanding the ideal gas laws is really what this unit is about. And so first we have to understand what an ideal gas is, and how gases behave in a little more detail than what we've learned before. So first we're going to talk about size. We know that they're tiny particles. They're so small they're considered to have no size relative to each other. And they are far away from each other. They're spaced out. They sometimes collide, but they're very small particles that are spaced out quite a ways from each other. And they have no attraction or repulsion. So they're not positively or negatively charged where they're attracted to each other or pushed away from each other. Okay, then we're going to get into their motion. So particles are in constant, rapid, and random motion in whatever container we put them in. And when they collide, no energy is lost. We call that elastic collisions. You don't need to really know that. We'll talk more about elastic collisions if you go on and take physics. And when they collide with the walls of a container, they cause pressure, and that pressure pushes on the outside of the container. A good example of this is if I blow up a balloon with air, every time the air molecules collide with the walls of that balloon, they cause pressure, and that's what helps the balloon keep its shape, and you can feel that pressure if you push on the balloon. Their energy, the kinetic energy of gases is determined by this formula, 1/2 mass times velocity squared. We're not going to deal a lot with kinetic energy in here. You would learn about this in physical science or in physics. M is mass, V is velocity in that equation, and temperature is a measure of the average kinetic energy of the gas particles, and we deal with temperature in chemistry, and that's how we look at the energy of gases, is their temperature. All right. And we're going to talk next about pressure. You can see here the formula for pressure is force divided by area, and it's measured using a barometer, and that's what this is on the right hand side. So a barometer is filled with mercury. It's a liquid at room temperature. You can see there's a pool of it here, and air pushes on that pool of mercury, and it is able to go up in the tube up to the amount of pressure that the air is at, and that's how a barometer is used. Sometimes on the news you'll hear them talk about the barometric pressure, and pressure tends to change when we have a front going through or a significant weather change. These are the different units of pressure. It says that you'll need to be able to convert between these units. These are on your cheat sheet on the back. Okay, and so you don't have to memorize these. You'll have all of them. So we have atmospheres, kilopascals. Notice that the P is capitalized in this. Millimeters of mercury. We have torr. We have PSI, which is pounds per square inch. We have inches of mercury, and we have pascals. So pascals and kilopascals, you can notice they're very similar. This is 1,000 pascals, so that's why our decimals moved over. Okay, and it's all compared to 1 atmosphere. And really what that's, 1 atmosphere is how much pressure we have if you were to stand at sea level. And all these values are equal to each other, so we can convert between them using dimensional analysis. So we need to be able to convert, so we're going to do a conversion here. We're going to convert 540 millimeters of mercury to pascals. So we start with what we know. You can think of our crisscross or our train tracks here. We have 760 millimeters of mercury to 101,325 pascals. So if we take these and multiply, divide by this one, we get 71,994.08 pascals. And you're going to notice we're going to round to the hundredth place just like we've been doing before. All right. The second example says to convert 50 psi to atmospheres. I want you to pause the video, try this one, and then come back, press play, and check your answer. So this one, PSI, there's 14.7 PSI in 1 atmosphere. There's our dimensional analysis, and we get 3.40 atmospheres. Last example, if a balloon has a pressure of 1,205 torr, how many kilopascals does this equal? Again, pause the video, try this, and then check. We have 760 torr in an atm is equal to 101.3 kilopascals. And so when we do our math, we get 160.61 kilopascals. And you'll get a chance to try some more of these on your homework. Okay, the next thing we're going to talk about is just a review of temperature. Absolute zero is the lowest possible temperature. We think of that as 0 Kelvin here. You can see it compared on the other scales. That would be like negative 459 Fahrenheit, which would be very, very, very cold. Absolute zero is considered the temperature when molecules stop moving. Okay, and you can see we have our targets in Celsius. We have 0 as when water freezes, which is 32 degrees Fahrenheit, and it boils at 100 degrees Celsius or 212 Fahrenheit, and then you can see the Kelvin scale. Okay. Again, absolute 0, 0 Kelvin, or negative 273 Celsius. We talked earlier in our stoichiometry unit about STP. STP is standard temperature and pressure. So when you see that, it means that we're dealing with a temperature of 0 degrees Celsius or 273 Kelvin, and that pressure is at 1 atmosphere. And we know that there's all those units that are equal to 1 atmosphere, so it could be in the other units as well. But that's what standard temperature and pressure, or STP, means. So we need to be able to convert between temperatures. So if we want Kelvin, we take the Celsius and we add 273. If we want Celsius, we take Kelvin and we subtract 273. We're not going to worry about converting to Fahrenheit, just between Celsius and Kelvin for this class. So if we're going to convert 400 Kelvin to Celsius, we're trying to get Celsius. We're going to take our Kelvin and we're going to subtract 273, and we get 127 degrees Celsius. Example 2 says to convert 60 degrees Celsius to Kelvin. You can pause and try this one. To do this one, we're starting with Celsius and trying to get Kelvin. So we take our Celsius and we add 273, and we get 333 Kelvin. Okay. Next, we're going to talk about diffusion. So this one, we're doing the class, so you're not here for this. And so you can skip this in there, but what we're doing, if you want to answer these questions, you certainly could. But I have a hot beaker and a cold beaker, hot water, cold water, and I'm going to add a drop of food coloring to each, and I want you to think of what would happen. And what should happen is that when you put it in the hot, it mixes up quite quickly throughout the water. When you put the drop in the cold, it goes all the way to the bottom, and you can almost see the exact path of the food coloring drop. And so what's happening on the macroscopic or the visual level is that what we see, which we just talked about, at the particle level, you're seeing those liquid molecules spread out in the hot and stay together with the cold. And then what do you think they'll look like by the end of class? If we left until the end of class, they would both evenly diffuse or spread around, because that is what happens over time. It just, the cold takes longer for it to spread than the hot does.